My work today is going to focus on ion exchange technology, specifically the regeneration. Then I'm going to look at an alternative salt to regenerate with bicarbonate instead of sodium chloride. And all of this is in the context of NOM removal, natural organic matter removal, in the production of drinking water. So the context of this is the same treatment plant that we just heard about, the treatment plant in Ondijk. And in this case, we're using ion exchange to remove DOC as a first step in our treatment in order to improve the treatability for downstream treatments, which are ceramic microfiltrations and advanced oxidation with UV and H2O2. So in that case, we're going to try to reduce the OH radical scavenger and increase the UV transmittance. To do so, we're using a strong basis anion exchange resin provided by Lanxess. So just because the plant is the first step in our drinking water, we cannot use classic ion exchange columns. So we're using the suspended ion exchange. And the way this works is that we're going to dose resin at the entrance of the contactor, just 15 milliliter per liter. And then the resin and the water will travel together through the contactor for 30 minutes contact time. And the resin is kept in suspension by the implementation of air bubbles, what we call an airlift. And during that time, what's going to happen is that every anions from our surface water is going to absorb onto the resins, and in exchange, the chloride that is preloaded on the resin is going to dissolve in the water. So furthermore, the resin is being separated from the water in lamella separator, and the water goes to the next step of treatment, while the resin is being collected and regenerated just right away. And to do so, we just reverse the previous operation by just introducing the resin to concentrated sodium chloride, and then the gradient concentration is going to dissolve every ions on that resin, and then the resin is ready for next cycle of anion exchange. So that process works well in Ondijk so far, at least for DOC adsorptions. In this series of slides, you'll see the concentrations in the effluent and effluents. So influent is the isolate in blue, effluent is the yellow. And with DOC adsorption, we could always achieve 52%. The water leaves our first treatment process with less than 3 milligrams per liter. As a result, we increase the UVT adsorption, which is our targeted compound, above 93%. But, as I mentioned before, not only DOC adsorbs on that resins, and our water is quite heavy with sulfate and bicarbonate, so we have a large absorption of sulfate and bicarbonate as well on the resin. And the main problem of this is not that we're going to mix sulfate and bicarbonate in the water, but it's that it takes the chloride exchange capacity. So that process participates quite heavily to the increase of sodium chloride in the treated water. So much that we are regularly above the Dutch water quality standards. And sometimes in the summer, we're actually getting quite close to the World Health Organization standards. So that is going to create a problem. And in the future, this is getting worse because we see that there's a salinization impact on our source water. This is due to climate change and increased human activity on that water. So here we are. We've got a process that's pretty good at DOC removal, which is our target. Hi, Daniel. But in exchange, participate heavily to the increase of chloride in our water. And the sad part of it, well, this is kind of specific to our water because the sad part of it is most of it is going to be exchanged for bicarbonate and sulfate, which are not targeted in the process. And yeah, that we can't really remedy because of the selectivity of the resin. But a potential remedy is to exchange our counter ions. And as you see in the selectivity range, bicarbonate and chloride are quite equivalently selective to that resin. Besides, bicarbonate is non-toxic, so that makes it quite a good candidate for exchange. So that's what we investigated in this research. The alternative regeneration of the ion exchange resin with sodium bicarbonate instead of sodium sulfate in order to reduce the chloride in our effluent water, but while keeping the removal of DOC as it is. And we're going to look at it from different angles. One is the kinetic of the adsorption, which is important. But not only, also the efficiency of the regenerations and the quality of the spent-bright solution that we produce as a waste brine. And finally, the sort of practical aspects of switching the salts. So we started the investigation on bench scale, was jar test. So we exposing 60 liters of our influent water to the two kinds of resins, one in chloride form, one in bicarbonate form. On the kinetic points, the advantage of kinetics is because we can follow the behavior of that resin in time. So you see the concentration here of DOC in the water in time. And what we see from that slide is that the resin in both forms, bicarbonate and chloride, react pretty much exactly the same. So we usually have quite some calculation we do in terms of a percentage removal or equilibrium value, or we calculate the kinetics according to different models. But in that case, it's just simple to look that both forms match completely. And this is true for chloride, but it's also true for sulfate and for nitrate. So we can come to conclusions that it doesn't affect massively the adsorption kinetics. The only difference, of course, is going to be for the chloride and the bicarbonate. So the resin in chloride form will release chloride here on the left and absorb bicarbonate. The resin in bicarbonate form would just release bicarbonate and absorb chloride. But what we see is that the two matches each other quite well. And if it looks a little bit like there's more bicarbonate being released than chloride, this is just a matter of molar mass, because those results are expressed in milligram per liter, but once you switch them to molar equivalent, you got exactly the same. This is also friends at Cranfield University who studied the same matter and got pretty similar results. They even went deeper into the fractions of NOM being removed, as well as into the formation of DPBs. The next step is also on bench scales, is the regeneration of that. I'm looking at the time, that's not going to do it. So I might just skip a few, because that's the main results. When we look at the pilot. So we tested the two results, not only on bench scale, but mostly on pilot scale. And in the pilot that we're using, they can treat 7 meter cube per hour. The pilot works exactly the same way as the full scale that I introduced to you earlier. We're using the same contact time and the same resins in the same concentrations. The resin we're using is initially in a chloride form. So what we did is, so initially it's being regenerated with 50 grams per liter of sodium chloride, but we introduced it to sodium bicarbonate, 84 grams per liter, and then in a view of optimizing that regeneration, we try to reduce it in time. So we've been running this for 4 weeks. This is mainly because the research happened in 2020, the same time as COVID happened. I'm going to also skip this to go directly to the continuous results. So this is the results within our 4 weeks of operations. And the first bar marks the time where we switch to the adsorption, to the regeneration from sodium chloride to sodium bicarbonate. It took about 2 days for the resins to completely switch to bicarbonate counterions. And the second bar will be the moment where we reduced the regeneration. So you can see in this sort of long-term operation is that the removal of DSC seems again absolutely not affected by any of these changes. And we can maintain our stable 50% removal that we had before, if you remember that graph from earlier in the presentations. And this is even truer if we zoom in that graph to a period of the year where it's the same kind of DOC in our influent water. Yeah, and the goal of this presentation was also to reduce the amount of chloride being released in our effluent water. So here you can see in the day -1, so the day before the transition, when the resin was operated in chloride, you had an important release of chloride in the effluent water, whereas after this, we could match a stable 30% removal of the chloride. So if you compare the two situations, chloride from resins versus bicarbonate from resins, that would be a 60% reduction of the chloride in our effluent water. So way below the Dutch standard that we couldn't match before. In exchange, we're going to increase the amount of bicarbonate in our effluent water quite a lot, plus 87% when we didn't optimize the regenerations, a little bit less when we did optimize the regeneration. But that just improves your alkalinity, which is not always a bad thing. As a summary of all the anions being removed during this process operations, we have 30% chloride removal, 33% of nitrate, which slightly decreased in time with the operations, in stable 85% of sulfates and 50% of DAC. That all of them could be stably removed during the 4 weeks of operation. Another aspect of the pilot operations is that we could look at the productions of the spent brine, the quality of the spent brine that we're going to have to dispose of a way or another. And what we see here is a spent brine that we produce at 84 grams per liter of sodium bicarbonate versus 65 grams per liter of sodium bicarbonate used in regeneration. And we see that we produce an increase of bicarbonate in our spent brine, which decreases with the amount we use, which is expected. But if you compare the other ions that are being dissolved during the regeneration, these do not decrease as we optimize the resin. So we can conclude that optimization still provides stable operation of our resin. So finally, in conclusions, what this research proves is a proof of principle that the alternative regeneration with bicarbonate is viable. We saw that in the adsorption kinetics with no change whatsoever in the way the resin behaved in absorbing these anions. And we saw that in continuous operation of the pilot, which could keep our 55% removal DOC. Meanwhile, we could reduce the desorption of chloride in our effluent water by 30% compared to influent water, or even 60% if you compare to current situation. The regeneration of resin was found effective. 65 grams per liter of sodium bicarbonate was found sufficient, and we don't have time to go further because of COVID, but there's possibility to further optimize that amount. But not everything is perfect, so if you look at the global feasibility, on the plus side, we have an improved water quality with a reduced chloride and improved alkalinity, which can also have for a positive effect to, I didn't do that. Sorry, it's gone there. But it's not gone there. Which has for a positive aspect to increase the corrosion index, decrease the corrosion index in your pipes. The spent brine that's being produced in comparison with the sodium chloride has a reduced impact on the environment and an increased alkalinity, which makes it actually very compatible if you want to discharge this in a wastewater treatment plant. It's actually alkalinity increase is something they're going to be looking for. So that is massively going to reduce your cost of disposal. But on the negative sides, the operations might be a tiny bit more complicated. One way is that sodium bicarbonate is a powder, as opposed to sodium chloride, which is manufactured as like rock salt. So that's harder to handle. We have problem with the solubility, way lower solubility of sodium bicarbonate compared to sodium chloride, which also might decrease in colder temperature. So in the Netherlands, the winters are quite cold, that might be a problem. The dissolution of the sodium bicarbonate also much slower, so something to take into account. With the possibility also to have formations of precipitates, and as well as the fact that the carbonate can be used as a source for biogrowth. And the most important one would be the cost of the salts. Due to this new method, we have an increased use of salts because it's just heavier than the sodium chloride was, and you pay your salts per ton. So that's a factor, in addition to which the sodium bicarbonate is just more expensive than the sodium chloride. So we might look at a 6-time increase of your chemical costs in the process. Bye. Thank you for your attention.